Hi students, welcome to the third lecture of Basic Mechanical Engineering. And in the previous lecture we have studied the classification of thermodynamics and its application, and we have discussed about state, properties of a system, equilibrium conditions, process, parts, etc. And in this lesson we are going to discuss about heat, work and internal energy of a system. So first of all, we have to define what is a cycle, what is a thermodynamic cycle. When a system in a given initial state experiences a series of processes and returns to its initial state, that system undergoes a cycle. We can say that the system undergoes a cycle, and at the end of the cycle the properties of the system have the same value they had at the beginning. That means in this figure we can see that initially it is at state 1, the system is at state 1, and then move to state 2, then to state 3 and to state 4, and finally come back to state 1. Then we can say that that the system completes a thermodynamic cycle. That means when a series of changes happened in the system and it's come back to its original position, then we can say that it is a thermodynamic cycle, or it completes a thermodynamic cycle. And thermodynamic path in a cycle is in closed loop form. That means it is a closed loop, 1, 2, 3, 4 and 1. So it is a closed loop. Okay, so a thermodynamic path in a cycle is a closed loop form. Okay, and also cyclic integral of any property in a cycle is 0. That means the initial and final states are same. So the cyclic integral of any property in a closed cycle gives 0. That means cyclic integral dp equal to 0. So and p is any thermodynamic property. So this is a cycle. This is called a thermodynamic cycle. And what is heat? Actually, we already discussed that heat and work are energy in transit. That means the energy transferred in form of heat and work. Okay, so it is defined as the form of energy that is transferred between two systems, or a system and its surroundings. We can see that here it is a baked potato with some temperature, and surrounding has air and it has a lower temperature. Because of this temperature difference, what happened, that heat energy leaving the system to the surroundings. So the temperature difference causes the heat to flow. Okay, so heat is an energy in transit. Okay, so temperature difference causes the heat energy to flow from higher temperature to lower temperature. Okay, and by virtue of a temperature difference, the transfer of heat into a system is frequently referred to as heat addition, and transfer of heat out of the system, that is termed as heat rejection. Okay, and heat is transferred in a system to surrounding in 3 ways: conduction, convection and radiation, and a process during which there is no heat transfer, and such process is known as adiabatic process. A process during which there is no heat transfer, that process is known as adiabatic process. Next one is work. Work, like heat, is an energy in transit, or energy interaction between a system and its surroundings. Okay, so consider that this is a system and heat is entering the system. That means heat is represented in Q. Q in means heat is entering the system, and Q out means heat is leaving the system, and W in means work energy is entering the system. W out means the work energy is leaving the system. So work is another form of energy in transit. Like heat, work can also interact from system to surroundings. So positive work is done by a system when the sole effect external to the system could be reduced to the rise of weight. Okay, that means when a system doing work, it is considered as positive work, and we are doing a work to the system, it is considered as negative work. Okay, so work is the energy transfer associated with a force acting through a distance. Work means when a force is acting and it causes the system, or it causes it to some body to move, then a work is happening, work is done on the system. We can say that work is done on the system. For example, raising a piston, a rotating shaft, and an electric wire crossing the system boundaries are all associated with the work interactions. That means when we doing some work to the system, or the system is doing some work outside, these are the work energy transfer between system and surroundings. So what do you mean by work done? Consider a cylinder in which a small piston is inside that cylinder and a gas is filled inside the cylinder. And when we add heat or something on this gas, what happened? The gas will expand and exert and pressure inside this piston. Because of this piston, the piston move upwards, and there is a force. Okay, because of this, a piston moves upwards with a distance ds. Okay, so what is work done? Actually, work done is equal to force into displacement, right? So consider this. This is a pressure volume graph, and initially the piston is here at this position. Okay, and when the gas pressure increases, what happened? The piston moves from 1 to 2. Okay, and the piston reaches at position 2, and the pressure decreases because of this expansion. Okay, pressure decreases, and this is the process path. Okay, when the system moves from 1 to 2, state 1 to state 2, this is the path followed. And what is actually the work done? The work done is calculated. Work done is the area under the curve, area under this curve 1, area under this curve 1 2. So this is the area under this curve. So consider small area dA, which is equal to P into dV. dV is the small displacement. Okay, small volume. Okay, small volume change, and area dA is equal to P into dV. So what is the total? What will be the total work done? Total work done is equal to, from 1 to 2 is equal to integral of 1 to 2 P dV, or is equal to P into V, pressure into volume. So this is the pressure volume work. Okay, so actually work is done by the system. In here work is done by the system, because this gas is actually acting a pressure on the piston, and the piston is moving upward. So the work is done by the system. Okay, and sign conventions. Okay, so I already said that when work is done to the system, it is considered as negative work, and if work is done by the system, it is considered as positive work. And similar that work is heat energy entering the system is termed as positive, and heat energy leaving the system is termed as negative. Okay, so what are the similarities between heat and work? So heat and work are both recognized as the boundaries of the system. Okay, and both heat and works are boundary phenomena. Both heat and works are known as boundary phenomena because it acts on the boundaries of the system. So that means work and heat are crossing the boundary of the system. Okay, if energy transfer occurs between the system, then we can say that heat and works are energy in transit, and the system possesses energy but not heat or work. That means system has a temperature but not a heat. Okay, that means both are associated with the process, and both heat and work are associated with the process and not a state. Okay, so unlike properties, heat and work has no meaning at a state. Heat or work doesn't have a meaning at a particular state. When temperature difference occurs, heat is transferred from the system. Okay, and also when work is done on the system or done by the system, and work interactions happen there. Okay, so this is an interactive process. Work and heat are energy in transit. If something transfer from the system or transfer to the system, then we can say that those are heat and work. Both are path functions. I already said that heat and work are path functions, and it depends upon the path that it follows. Okay, and their magnitude depends on the path followed during a process as well as the end states. Heat is low grade energy and work is high grade energy, because low grade energy means heat, when a temperature difference occurs, heat easily dissipates to surroundings, so it is known as low grade energy. Okay, next one, forms of energy. I already said that there are so many ways we can create energy. Okay, so energy can exist in numerous forms such as thermal energy, mechanical energy, kinetic energy, electrical energy, magnetic energy, chemical energy, and nuclear, and there some constitute the total energy E of the system. So total energy is equal to total macroscopic energy plus microscopic energy. Okay, thermodynamics provides no information about the absolute value of total energy. It deals only with the change of the total energy. That means total energy of a system has no significance. The only significance is that how much change occurred on that energy, total energy of the system. Okay, so that constitutes a new terms known as energy balance. So the net change means increase or decrease in the total energy of the system. I already said that the change in energy of the system has the significance, and net change in the total energy of the system during a process is equal to the difference between the total energy entering the system and the total energy leaving the system during that process. When a process is happening, some energy entering the system and some energy leaving the system. So total energy means change in the total energy of the system means total energy entering the system minus total energy leaving the system, or E in minus E out equal to delta E of the system. Okay, or change in the total energy of the system. So this relation is often referred to as the energy balance, and it is applicable to any kind of system undergoing any kind of process. So this is known as energy balance, and this equation is known as energy balance equation. Next term is internal energy. I already said that when total energy means total energy of the system entering the system and total energy leaving the system. So already, and also it has a macroscopic energy and microscopic energy. The macroscopic forms of energy are those a system possesses as a whole with respect to some outside reference frame such as kinetic and potential energies. So macroscopic energy means that system possesses at a whole completely. System possesses completely because of its movement velocity and its height difference, etc. And that means kinetic energy and potential energies are some macroscopic forms of energy. And microscopic energy means are those related to the molecular structure of the system, or in a molecular level, the movement of the molecules, activities, the interactions, and these are the microscopic energies, and they are independent of outside reference frames. That means the sum of all the microscopic forms of energy is called internal energy. The sum of all the microscopic forms of energy, That means the sum of all the interaction between the molecules of the system, and that is known as internal energy of a system, and it is denoted by U. Okay, so total energy of system is equal to E is equal to internal energy plus kinetic energy plus potential energy. That means U is U plus M into V square by 2 plus mg into Z, and energy is in kilojoule. So we are only bothered in the energy change of the system. So energy change means delta E system means energy at final state. When a state change from another state, the energy change means energy at final state minus energy at initial state. Okay, so E system is equal to E final minus E initial, or E2 minus E1. That means delta is equal to delta U plus change in internal energy plus change in kinetic energy plus change in potential energy. So change in internal energy means M into U2 minus U1, where U1 and U2 are specific internal energies of the system, initial and final states. Specific internal energy means internal energy per unit volume. Unit mass. Internal energy per unit mass. That is why we are multiplying it with the mass. M into U2 minus M into U1. Kinetic energy is equal to 1/2 into M into half M V2 square minus half N V1 square. Potential energy is equal to mg into Z2 minus mg into Z1. So when we are dealing with the stationary systems, therefore potential energy and kinetic energy will become 0. So total energy of the system is equal to total internal energy, change in energy is equal to total internal energy change only in a stationary system. Mechanisms of energy transfer. That means E in and E out. Consider a system. The energy can transfer from one system to the surrounding in the form of heat energy, work energy, and mass flow. Okay, so mass flow means entering the mass of the quantity, any quantity entering the system. Okay, and it is leaving the system. And also work interactions, work entering the system and work leaving the system, or heat entering the system and heat leaving the system. Work is done for the system and work is done by the system. Okay, so the only two forms of energy interactions associated with a fixed mass or closed system are heat transfer and work. For a fixed mass system, that means mass is not entering the system or leaving the system, so it is a closed system. So in a closed system, only interactions are heat energy and work energy. So the net transfer of a quantity is equal to the difference between the amounts transferred in and out. The energy balance can be written more explicitly as E in minus E out. Total energy entering the system minus total energy leaving the system is equal to total heat energy entering minus total heat energy leaving the system plus total work entering minus total work leaving the system plus total mass entering the system minus total mass leaving the system. That means which is equal to delta E of the system. When we say that it is a closed system, E mass in minus E mass out becomes 0. So delta E, total energy change, is equal to delta Q plus delta W only. And for a closed system, delta E system becomes 0 and E2 minus E1 becomes 0. That means delta E is equal to delta Q plus delta W, or delta E becomes 0. That means in a closed system does not involve any mass flow across its boundaries. Therefore, the energy balance for a cycle can be expressed in terms of heat and work interactions. Okay, heat and work interactions only. That means delta E becomes 0 and delta Q equal to, or W net out equal to Q net in, or total heat energy is equal to total work transfer. Okay, so this is in the case of a cyclic process, closed system undergoing a cycle, because initial and final states are same, and because of that delta E of the system becomes 0. So you have already studied this thing, enthalpy. What is enthalpy? Enthalpy is the measure of the total energy of a thermodynamic cycle or system. So it is the sum of the internal energy and pressure volume product. So enthalpy is represented as H and it is equal to sum of internal energy U plus P into V, pressure volume product, where U, P, and V are the point functions. So H is also a point function and a property of the system. So enthalpy is the property of a system. And enthalpy of an ideal gas is also a function of temperature. Enthalpy is a function of temperature also. And unit of enthalpy is in kilojoule, because this is the internal energy and the pressure volume. Also, all are works. Okay, and energy, work energy. Because of this enthalpy, unit of enthalpy is kilojoule. And there is another term known as specific enthalpy. That means specific enthalpy is represented as H, small letter H, and is equal to small letter U plus P into V. Okay. Next one is entropy. So what is entropy? Entropy means disorder. When something happening on the system, the change, it has a molecular change occurred on the system, and when that occurred, there is a disorder occurred on the system, and that measure of this molecular disorder or molecular randomness is known as entropy. Okay, a system becomes more disordered, the position of molecules become less predictable, and the entropy increases. That means consider a closed system and we are heating that system. What happened? The molecules of that system gets some energy, and because of this energy it moves random. And when the heat and when the temperature rises, this that energy possessed by the molecules increases and it moves more randomly, and that disorder is known as entropy of the system. Okay, when temperature increases, the entropy increases. Okay, system become more disordered, the position of the molecules become less predictable and the entropy increases. Thus it is not surprising that the entropy of a substance is lowest in a solid phase and highest in gaseous phase. That means entropy of a substance is low when it is in solid phase. That means when an ice cube changes to water, the entropy increases. Okay, and that water changes to ice again, and its entropy decreases. Okay, so entropy is the thermodynamic property of a working substance that increases with the increase in temperature and decreases with the decrease of temperature. Entropy can be measured directly, but the change in entropy during any process can be calculated. So we are more interested in the change in entropy of system, and entropy is the point function. Okay, it depends upon the state of the system. Okay, so entropy is represented, change in entropy is represented as ds, which is equal to delta q by t or dq by t. Okay, so these are all today's lecture, and go and study these terms in details. That means heat, work, internal energy, entropy, etc. So we can see in the next lesson. Thank you.